All right, welcome ladies and gentlemen. This is video number 3 for chapter 4, solution stoichiometry. And in this video I'm going to talk about molarity, the formula for molarity, calculating molarity, and how it relates to concentrations of ionic compounds, and therefore ions in solution, as well as dilution, what that means and how we can actually calculate that. So molarity is something that you saw before in Regents chemistry. Molarity is defined as moles of solute per liter of solution. So the formula looks like this: moles of solute on top, liters of solution on bottom. It's a formula, yes, but I consider this more of a definition. This is literally what molarity is. It's moles per liter. We abbreviate it as the capital M here. And notice that in our definition, it does have to be in liters, not milliliters. Milliliters are going to be a much more common unit given to you for the volume of a solution. So you will have to convert to liters in order to do the calculation for molarity. So just remember that 1,000 milliliters are equal to 1 liter and work that way. That's actually a calculation you don't really need to show, but if you're ever unsure like which way you go, I always recommend doing a T-chart. Remember 1,000 mils in 1 liter. Be very, very comfortable. I'm not even going to go through a simple molarity calculation, but you should feel comfortable calculating molarity from if I give you grams and milliliters. If I give you grams of solute and milliliters of solution, right? We'd want to go grams to moles via GFM to get the numerator in the molarity definition, and then mils to liters via 1,000 mils in 1 liter, and calculate molarity that way. Because this is a super common type of calculation. They say, oh, we've got 10 grams of sodium chloride in 475 milliliters of water. What's the molarity? You should feel comfortable doing that. The big point that I really want to make about molarity is it is actually a new tool for our stoichiometry toolbox. Just like if you have grams, if I give you grams in a problem, if I give you grams of a compound, we should be automatically thinking, okay, turn it to moles through gram formula mass. That should be an automatic now. We have a new automatic. If you are given molarity and volume, that very specific combination of information, molarity and volume. If you are given molarity of something and the volume of something, if you're given the concentration and molarity of that thing and the volume of that thing, based on the definition of molarity, which is molarity equals moles per liter, right? You have this, guess what? You really have moles. Molarity and volume together, that combination of those two numbers, those two pieces of information for a solution, is a very common combination of numbers. So we need to understand that if we are given this special combination of numbers, that means that we actually have moles. And I guarantee you, you will need to calculate moles in the problem. I lay down my life that if they give you molarity and volume, shocker, you should calculate moles. So this is a new entryway into stoichiometry problems. If I give you this combination of numbers, molarity and volume, let's get moles, and then let's do some stoichiometry with it. So just as an example, 400 milliliters of a 0.2 molar, and that's how you read the capital M, 0.2 molar NaCl, it really means when I see this combination of numbers, right, 400 milliliters, 0.2 molar, let's figure out how many moles we have. So actually doing this without a calculator, right, 0.20 molar, x moles over 0.400 liters. Now, obviously I know that I'm going to be multiplying these two numbers together in order to solve for moles. Multiplying those, basically doing this math without a calculator. Because this is something that I expect you to be able to do without a calculator. The way that I do this without a calculator is I basically move the decimals, because the decimals are what's making it hard. It's not the 2 and the 4. The 2 and the 4 is easy, but it's the decimals that make it hard. If I sort of move the decimal on the 0.2 one place that way to make it 2, because 2 is a nicer number, and then I move the decimal one place that way on the 0.4 to make it 4, which is a nicer number, and then I multiply them together, right, I get 8, but the decimal's here. Then you kind of have to undo the decimal moving that you did. Now I moved it 2 places, so now I got to move it 2 places back. So the answer is 0.08. moles, and that's how I do that sort of math without a calculator. It's basically like I move the decimals and I count the number of places I move them. I move the decimals to make the math easy so that I can do it in my head, and then I just move the decimals right on back when I'm done. And I know, I feel confident that I have the correct decimal place. So the 400 milliliters of a 0.2 molar solution really means 0.08 moles. That's really what it means, and that's the number that I guarantee you we do more work with. But remember as well that NaCl 100% dissociates, right? It's a strong acid. It's a strong electrolyte. It's a soluble salt. So it's not really NaCl in solution. It's really Na plus and Cl minus. So what we really have, 400 milliliters of a 0.2 molar NaCl solution really means 0.08 moles of Na plus and 0.08 moles of Cl minus, because, right, this is going to dissociate into this and this. So this is a 1 to 1 to 1 ratio. So 0.08 moles here means 0.08 moles for the Na and 0.08 moles for the Cl minus. So we can very quickly go from molarity to concentrations of ions. But the thing is, we don't have to do this concentration of ions just with moles of the ions. We can actually do this with molarity as well. If the volume of solution is not changing, if you know that you're not like adding more water to it or removing any water from it, if the volume is staying consistent, then this idea of molar ratios will hold for molarity as well as moles of a compound. So for example, for a 2 molar NaCl solution, right? And we know that NaCl dissociates into 1 sodium ion, 1 chloride ion, so just writing it out like that, this is a 1 to 1 to 1 ratio. So 1 mole of NaCl makes 1 mole of Na plus 1 mole of Cl minus. But molarity is moles per liter. And if the liters are unchanging, if you are not altering the liters in your solution at all, then we can say that this 1 to 1 to 1 will hold true for concentration as well as moles, because molarity is moles per liter. So molarity is directly related to the number of moles you have, which means that a 2 molar solution of NaCl actually means that you have a 2 molar concentration of Na plus and a 2 molar concentration of the chloride ion, right? If the problem is not at all saying that you are changing volume or adding volume in any way, then your molarity ratios are actually going to be the exact same thing as your mole ratios if volume is sort of taken out of the equation. So just proving my point, one more example, for a 0.25 molar calcium chloride solution, concentrations of ions, well, calcium chloride dissociates completely, it's a soluble salt, into calcium ions and 2 chloride ions. Remember, careful of the subscripts. And therefore, if you have a 0.25 molar concentration of this, and we're in a 1 to 1 to 2 mole ratio based on the coefficients, I know I'm also going to have a 0.25 molar concentration of the calcium ion, but I am going to have a 0.50 molar concentration of the chloride ion based on the mole ratio. So basically the really big point. Our concentrations of ions are 100% based on our stoichiometric coefficients, because molarity is moles per liter. If liters are staying unchanged, then there's a direct relationship between molarity and moles, and we can use that to work out concentrations of ions. And then the last thing, dilution. Dilution, hopefully you're somewhat familiar with the concept of dilution. If you dilute something down, if you think about a really like diluted drink, like a drink mix, like those, lemonade powder drink mix or Country Time lemonade, if it's really, really dilute, it tastes super watery. You're not actually tasting the lemonade as much, you're tasting all the water that went into it. So to dilute something means to add water to a solution to basically increase the volume of the solution, which would then decrease the concentration of the solution. Because when you're diluted, your moles stay the same. Moles of solute are unchanged. right? If you dilute something, you're adding water, but you're increasing the volume, right? You're adding more solvent. So, right, molarity is moles per liter. If moles are unchanged, so if moles stay equal, but you divide it by a larger number, then your molarity is going to go down. Molarity decreases. So when you dilute something, you are decreasing the concentration of that thing. But moles are staying exactly the same, and that is a huge, huge point. Dilution with water is not altering the number of moles of solute present. You are not changing that whatsoever. So our massive point is that when you dilute something, your moles of the solute before you dilute it is equal to your moles of solute after you dilute it, because that is absolutely unchanged. Now the molarity will change and the volume will change, but the moles will not change. So what we have from that is the dilution equation. M1V1 equals M2V2, where M is molarity and V is volume. And what this is saying is molarity times volume before you dilute it is equal to your moles of solute, right? Because molarity, up here, molarity equals moles over liters. If you multiply molarity times volume, you get moles. Moles times molarity times volume before you dilute it, that's the moles of your solute before, is equal to the molarity times the volume after you dilute it, because that is equal to your moles of solute after. So this is basically saying moles of solute before stay exactly the same as the moles of solute after. This is a really important equation that we use for dilution, and I'm going to talk about this a little bit more in class when we discuss dilution in class. That I'm going to have you write into your reference table in a certain section, because it's actually not on your reference table, but it is definitely one to remember and one that comes up frequently. So M1V1 equals M2V2 for diluting solutions.